Hi everyone, welcome back to ACIB. Today we will be going over Introduction to Stoichiometry. The first concept to note is the mole unit. You might have heard of this as the Avogadro's number, but basically it's a number that we use to measure something really small because we can have a lot of it in one grasp. For those of you that already know the number, it's 6.02 times 10 to the 23rd. And this is often the unit that we use when we talk about atoms or elements because they're so small that we would have a lot of them in one single object. To give you a sense of how many that is, if we had 6.02 times 10 to the 23 pennies and decide to give away $1 million a day to every person on Earth, it would take more than 3,000 years to distribute all of the pennies. That's how big the mole unit is. However, it's also small at the same time. For example, 1 mole of copper atoms, which is the element or compound that we use to make those pennies, is only enough to make 24 pennies. And this is why we often use the mole unit to describe elements and compounds and how many we have of them. Next, let's talk about molar mass, molar volume, and STP. Because each atom has a different mass, the molar mass of each atom, that is, the mass of a mole of an atom, of that element's atom, is different. We can use molar mass to calculate how much a compound will weigh in the end if we know the molar mass of the atom. The unit of the molar mass is written in grams per mole. It's written in grams per mole. And this allows us to measure the mass of certain elements or compounds if we have 1 mole of them. For example, if you were to consult a periodic table, 1 mole of carbon atoms weighs 12.01 grams. This number is averaged from all the different isotopes of carbon. If you don't know what an isotope is, stay tuned because we will be covering that in a future video. Molar volume is very similar, except it is used to measure liters of gas. And in this case, it will be liters per mole because we're talking about volume instead of mass now. This is useful when we're dealing with a lot of gas molecules and the volume that gas takes up, because at STP, which I will explain shortly, 1 mole of gas takes up around exactly 22.7 liters of space. Now, you guys are probably wondering, I've been mentioning STP a lot, and I've introduced molar volume based on that, but what exactly is STP? Well, STP stands for Standard Temperature and Pressure, and it is 273 Kelvin, or 0 Celsius, at a pressure of 100 kilopascals. At this pressure and at this temperature, as I mentioned before, the volume of any mole of gas is always 22.7 liters. This is useful for later on when we are talking about gas-to-gas stoichiometry, if we want to figure out how many moles of a gas there are if we're just given a volume. Now I would like to introduce the empirical and molecular formulas. They are similar, but they're not the same thing. The empirical formula is the smallest whole number ratio of atoms in a given compound. For example, the empirical formula of C2H4 would just be CH2. And that's because we have 2 carbons to 4 hydrogens, which is the same thing as saying 1 carbon every 2 hydrogens. Now notice that I'm not saying the compound is CH2, I'm only saying that the empirical formula of said compound is CH2. The molecular formula, on the other hand, is just C2H4 and that's what we usually refer to the compound by. The molecular formula of a compound lists all atoms that make up one molecule of the compound, whereas the empirical formula, as mentioned before, only gives the smallest whole number ratio of atoms in a given compound. I would like to point out that only covalent bonds would have molecular formulas. This is because when we're dealing with ionic compounds, it's given as a ratio. For example, NaCl is table salt. But when we're talking about NaCl or table salt, we don't mean there's literally one Na atom to one Cl atom. We just mean that there is one Na atom per one Cl atom, which makes the compound NaCl a ratio in and it's of itself. That means that NaCl is the empirical formula, and the compound, which is an ionic one, does not have a molecular formula. Here's an example question with empirical formulas, and I apologize for my laziness because the EF at the end stands for empirical formula. 43.2 grams of carbon is combined with oxygen, and the new compound weighs 159.0 grams. Find the empirical formula of the new compound. The first step in solving this question is to find the mass of each element. So in this case, we have C, which is 43.2 grams, and we have O, oxygen, which would be 159.0 minus 43.2, because it is the only other element in this compound. And that leaves us with a mass of 115.8 grams of oxygen. If we have the mass of each element, then we can find the number of moles of each element. 43.2 grams of carbon at 12.01 grams per mole is 3.60 moles of carbon. 115.8 grams of oxygen at 16.00 grams per mole is 7.24 moles of oxygen. If you take a look at this, if you're good at math, then you might realize that 7.24 is almost exactly double of 3.60. And that's kind of what we're going for here. If we divide 7.24 over 3.60, we get 2.01, which means that for every carbon atom, we have 2.01 oxygen atoms. And that leaves us with a final empirical formula of CO2. Okay, molecular formula is an extension to the empirical formula. What do I mean by that? Well, let's take a look. A hydrocarbon has an empirical formula of C2H5 and a molar mass of 58.0 grams. What is its molecular formula? Well, the first step is to calculate empirical mass. So 2 carbons has an empirical mass of 24.02 grams, and 5 hydrogens has an empirical mass of 5.05 grams. If you add these guys together, the empirical mass of the whole compound, C2H5, should be 29.07 grams per mole of the element itself. And then the next step would be to find the whole number multiplier. To do that, we divide the molar mass of the hydrocarbon by its empirical mass. So we have 58.0 over 29.07, and that gives us around a whole number multiplier of 2. Therefore, if we multiply the empirical formula by 2, we end up with C4H10, which is our molecular formula. The last thing I wanted to talk about in this video is percentage composition. Percent composition of a substance is the percent by mass of each of the constituent atoms of a compound. So percentage composition would be the mass of the atoms divided by the mass of the compound. An example question we have would be, what is the percent composition of Na2CO3? Well, first, we assume that there is 1 mole of the compound. And then we find the molar mass of Na2CO3, the mass of 2 moles of Na, 1 mole of C, and 3 moles of O. 1 mole of Na2CO3 should be 106.0 grams. And then 2 moles of Na should be 46.0 grams. The 1 mole of C would be 12.0 grams. And 3 moles of O gives us 48.0 grams. If we look at the percentage composition of Na, that would be 46.0 divided by 106.0, which is approximately 43.4%. For the carbon, it would be 12.0 over 106.0, which would be 11.3%. Lastly, for the oxygen, because it's the heaviest element here and there's the most of it, it would be 48.0 divided by 106.0, which would give it 45.3% composition. Note that percentage composition is calculated with mass, whereas the empirical and molecular formulas are calculated with the quantity of atoms or the elements inside the compound. Make sure to not get them mixed up. Alright, that's it for this video. If you like the content that we make, please remember to like and subscribe, and we will see you in the next video.